So welcome back to Chapter 6. Now, in Chapter 6, we're going to be talking about this normal probability distribution. And in order to start off with that, we have to start on Section 6.1, which is a standard normal distribution. Now, in Chapter 5, we were talking about discrete probability distributions. And in this section, we're going to be talking about continuous probability distributions. All right, so far we know that quantitative data can be split into two categories, one being discrete, one being continuous. Chapter 5 dealt on the data being discrete, how to display it, how to interpret it, how to find the center of measure and the spread. And in this section, we're going to focus on continuous data, again, how to find the measure of center and how to determine the spread. So, in order to talk about the standard normal distribution, we first need to talk about the density curve. And that density curve is given by the definition here. All right, so there we are. And let's actually, technical difficulties here. It's okay. All right, so when we start looking at this to find that we're looking at a density curve, what we want to do is we want to establish what is that density curve that we're looking at. All right. Now, the density curve is going to have some requirements for this continuous probability distribution. And those requirements are going to be that all of the probabilities must be between 0 and 1. And that's what this says here. The second part is that all of the added probabilities must be equal to 1. Now that should sound very, very familiar because when we looked at the problem back in Chapter 5, when we were trying to determine what is a valid probability distribution, we had the exact same requirements. Now, the first type of probability distribution that we're going to be looking at is going to be a uniform probability distribution outlined in this example here. Now, in this example, we have that the bus to Union Station leaves every 30 minutes and is uniformly distributed. Find the probability that a randomly chosen person arriving at a random time will wait between 10 and 15 minutes. All right, so probability notation wise, the notation that we're given is here. We want to find the probability that some random person, that means some random x value, will be waiting between 10 and 15 minutes. Now, we say that the bus leaves every 30 minutes, which means the probability of the bus leaving during any given time interval should be 1 out of 30. Now, if we're looking at the interval between 10 and 15, then we have to analyze what is this time interval. Well, that time interval is just 5. Now, looking at the height interval, what is that height interval here? All right, that's going to be that 1 out of 30. That's a probability. Now, in order to find this, we're then going to say, okay, well, finding the probability just means in our terms that we need to find this area for that rectangle. Well, how do we find areas for rectangles? We multiply length times width. And in this case, it's going to be 5 times 1 over 30. So multiplying 5 times 1 over 30, that should be 5 divided by 30. So I'm going to rewrite this down here. This is just 5 divided by 30, which then simplifies to 1/6. And if we look at this probability 1/6, we could approximate this to be 0.167 approximately. So in other words, as we're looking at this probability, we can say, or we can interpret this then, that a random passenger or a random person arriving at that bus stop will wait between 10 and 15 minutes, that probability being about 16.7%. All right. Now this again only works if we have a uniform probability distribution. Typically, when we work with probability distributions, it's rare to have these uniform probability distributions. And if you remember back in chapter 2, when we were discussing the different shapes that distributions can take, uniform was one of those values, or was one of those options. Now, a normal distribution. This is one that we want to focus on. So a normal distribution basically says that we have a continuous random variable that has a normal distribution if the density curve is symmetric and bell shape. All right. Now, they actually give us an equation for this. The equation that is given for this, I'm actually going to highlight this in like a light blue setting. Now, it's not something that we're going to be used to working with in this class, but if you're going to study more statistics down the line, or if you're going to see higher level math down the line, this is going to be an important equation that you want to observe. So I want to show you a quick representation of what does this curve look like when we're trying to graph it. So here's that curve. I actually took the curve and I put it on here, graphing this using my center or my mean as a standard distribution, meaning that I used my center, my average, my mean as 0, and then my standard deviation was simply just 1. So here, looking at this curve, my standard deviation is 1 and my measure of center is 0. Now again, this is going to be interesting because the x-axis now is interpreted as standard deviations. But check this out. When we use higher level math to actually find the area beneath this curve and above the x-axis, we actually get that total area is equal to 1. Now, that kind of stays in line with what we were looking at a little bit before, using the requirements for this distribution. The requirements for the distribution said that all of the summations of all of the individual probabilities had to be 1, and here it is mathematically. All right, so it's important for us to identify that when we have this bell-shaped, and if we have this bell-shaped curve, then there's an equation associated with it. But for our class, we don't need to know that equation. All right, so now that we have that visual representation, let's go through and let's see this example. This example says that the weights of all firefighters are normally distributed with a mean of 200 pounds and a standard deviation of 7 pounds. So what's the probability that a randomly chosen firefighter weighs between 185 pounds and 195 pounds? Well, in order to do this problem, what we're going to do is we're going to start analyzing, or we're going to start extracting the mean and the standard deviation. So I'm going to go through and I'm going to highlight what I need here. So let's highlight what we need. We have a mean of 200 pounds. All right, awesome, mean of 200 pounds. And then we also have a standard deviation of 7 pounds. I'm going to go through and I'm going to interpret that here. So we have a mean of 200, standard deviation of 7, which means this next tick mark is 207. The next one's 214. The next one's 221. Very nice. Now, if we wanted to go backwards, all we're going to do is we're going to subtract 7. So what I get here is 200 minus 7 gets us 193. And then 193 minus 7 should get us 186. And then 186 minus 7 should get us 179. Now, when we start observing this, we're going to say, okay, well, let's look at what they're really asking us. They're asking us to find the probability for a firefighter that weighs between 185 and 195. So 185, that tick mark should be somewhere here, and then 195 should be, well, somewhere between here. All right, so let's see, 195 probably somewhere here, which then means that in order to find this probability is just this shaded region. So, how do we then interpret this? Well, we interpret this way. We say the probability that some random firefighter chosen will weigh between 185 and 195 pounds is going to be roughly, and then we'll make some sort of estimate. All right. Now, I'm actually going to leave this blank at this point in time, because at this point in time, we don't have a really good, let's say, method for finding this probability, because this is a continuous probability because it deals with weights. With that, let's say, conundrum, we have to develop this a little bit more. So we will come back to this, hopefully in a little bit, and we'll actually get to find out what is that probability. So let's look at this standard normal probability. When we're working with the standard normal probability, what we want to do is we want to identify what is the mean and what is the standard deviation. Typically, when we're working with a standard normal distribution, uses the mean of 0 and the standard deviation of 1. So this definition is really, really important. That any time that they're giving us the standard normal distribution, it means that the bell curve is centered at 0 and it has a standard deviation of 1. Oops, excuse me, not -3, but +3. There we go. Which means empirical rule kind of applies here. If we look within one standard deviation, then we get about or approximately 68% of the data. Within two standard deviations, approximately 95% of the data. 3 standard deviations, approximately 99.7% of the data. So here we still get kind of this empirical rule process, which is kind of nice. Oops, excuse me. So this was the empirical rule back from chapter 3. Now, moving forward, the methods that we need to develop are going to be on this blue highlighted section here that I was dealing with this equation. Now, your calculator, your TI-84, has that equation built in, and all we have to do is just call upon that function. So there's going to be no need to program that function in because, again, somebody already took the time, programmed it in there, and just made a user face so that we can use it. One of the methods is going to be to find the standard deviation. The other method is going to be to find the y values. Now, when do we look at that, or how do we look at that? Well, the way that we look at this is going to be here. The important notes that are analyzed here is that the z-scores are the horizontal axis. So anytime that we have the horizontal axis, this means kind of like your x-axis. It's no longer the x, but it's going to be the z-scores. The next important topic here says that the area underneath the curve is equal to the associated probability of occurrence. That just means that the area underneath the curve references a probability. Now, there are two ways to find the area. And I'm going to be clear here that I am not going to use tables. Now, if you look at the formula card that I have on Canvas, that was the formula card that I handed out on exam 1. That formula card has certain tables on it. We are not using those tables. Our preferred method is going to be to use the calculator to find these z-scores, or to find the area underneath the curve. So if we want to find the area underneath the curve, we're going to use this command on the calculator. If we want to find the z-scores, then we're going to use this command on the calculator. Notice two different commands. Again, both of these commands use that formula that I highlighted in blue on the first page. All right, again, we're not using the formula on the first page, but we are using these embedded user interfaces that somebody programmed. All right, so we're going to go through and we're going to see how this works. So for the first question, part A, we have here that we want to find the probability given the following z-scores for a standard normal distribution. So really quickly, I'm going to identify what they're asking me. They're asking me to find the z-scores, and then they're telling me we have a standard normal distribution. Well, what does a standard normal distribution tell us? This tells us that the mean is 0. All right, that's going to tell us that the mean is 0 and the standard deviation is going to be 1. On a bell curve, what does that look like? It just looks like this. There we are. Just like that. Now, these are all z-scores, so I'm just going to label it z-scores. There we are. Now, I'm going to focus on part A. Part A is asking us to find the probability that z is less than 1.35. So all we need to do is identify where is 1.35 on this z-score number line. So 1.5 is here, 1.35 should be right below it, somewhere here. So I'm going to just draw a vertical line all the way to the top of this bell curve here, just like that. And then since the probability is less than that z-score, the z-score probabilities are less than 1.35, that means we're going to shade everything that's less than this z-score. So that means all of this area underneath the curve. And that's the part that we're shading. And because we're shading it, that means that we want to find that probability. So let's look at what we have here. In order to find the probability, that means we got to find the area. So if we want to find the area, we are going to use this one here. So we're going to have to go to the TI-84. We're going to go to second, VARS, and then distribution. All right, so let's access that TI-84. All right, here's the TI-84. So what we're going to do is we're going to go to that variation. Here we are. All right, but we want the distribution right up top. So we're going to hit second, distribution. There we are. And again, the distribution that we want is going to be that normal distribution. All right, so we want normal CDF. So we go down, find normal CDF here, that's number 2, and we're going to press enter. Now, what we want to do here for this normal distribution is that we want to enter the area that was shaded. The area that was shaded all the way to the left. Now, I'm really quickly going to go back and I'm going to talk about the areas quickly before I proceed with this TI-84. So, the areas underneath the curve here to the left and to the right, these tails don't exactly touch the z-axis. So they don't touch the horizontal axis. They just extend indefinitely. All right, meaning that it could have some end once it touches or it could not. Regardless of whether it touches or not, we can still find the area under that curve. So, anytime that we see the tail going off to the end on the left-hand side, the ending of the left-hand side is always going to be negative 1E99. Now, why is that? Well, The reason we always consider the left tail to be negative 1e to the power of 99 is because this is scientific notation, and using scientific notation, this is really negative 1 times 10 to the power of 99. This means that this here is a really, really large number. This is negative 1 multiplied by this number that has 99 zeros behind it. Wow. So that's a really, really extreme large number. And that's why we use that number on the left tail. If the area extended to the right and it encompassed the right tail, then we use the same number except we make it positive. So these two numbers are the two numbers that you always have to have embedded in your mind whenever you're dealing with probability under a curve. Because if it's the left tail, you're always going to remember left tail always needs to be negative 1e99. If it's a right tail, it must always be 1e99. And again, because on the TI-84, this E, capital E, means times 10 to the power of the numbers that precede it is the exponent. So now that we have a little bit more to work with, we're looking at this here, and the lower end, meaning the lower tail, is negative 1e99. The upper tail, this means where do we stop? What was that stopping point? Well, if you remember the stopping point for the z-score, that was 1.35. The mean that we were using was the standard normal distribution mean, which was 0, standard deviation 1. That's it. All we're going to do is press enter, and it automatically enters all of the information that I need. It says normal CDF. You want the left end to be really, really large negative number. You want to stop at 1.35. You have a mean of 0 and a standard deviation of 1. We press enter, and voila. We get our probability. This probability is approximately 0.911. So we're going to go back and write this. Now, before writing this down, we're going to make sure that we interpret what we have. In order for me to give you the credits on the exams, what I need to see is, I need to see that you were using some sort of command, in this case normal CDF. The lower end was that negative 1e99. The stopping point was this stopping point here, which was 1.35. The mean that we used was 0, and the standard deviation was 1. And again, this was approximately 0.911. So this first line here lets me know, hey, Mr. Castro, I know what I'm doing with the calculator. This is what I'm inputting. The second line then tells me, hey, you interpreted the answer correctly, which is a probability of 0.911. Awesome. Let's work on the next example. The next example, we want the probability that z is greater than 0.68. So let's first label our standard normal distribution. So labeling 0, 1, 2, 3, negative 1, negative 2, negative 3. Perfect. Now we want to identify the z-score of 0.68. So 0.68 should be somewhere around here, and I'm going to draw that up with a straight line. So that number there was 0.68. Perfect. And all I need to do now is interpret. What way do I need to shade? Am I going to shade to the left of this number or to the right of this number? If the z-scores are greater than 0.68, then I shade to the right. In other words, what kind of tail argument are we going to have? This is going to be a right tail argument because all of the data, or this probability that I'm looking for, extends to the right. So that means if this keeps on extending to the right, then I'm going to use 1e99 as the value that I want. So Let's practice on the calculator really quick. But before we go to there, let's see if we can write this out first. So normal CDF. All right, we're going to go from left to right. Left to right, what number do we stop at? In other words, what's that lower portion? Well, the lower portion of this area stops at 0.68. What's the upper portion of that area? The upper portion, we don't know where it stops at, so we just pick a really large number, and that's the right tail. Then we choose the mean and the standard deviation. The mean was 0, standard deviation was 1, because again, we're working with a standard normal distribution. And all we have to do is just enter this into the calculator. So here we go. Again, we want normal CDF, so we're going to press second, and we're going to go to distribution here. So second distribution, now we want our normal CDF. So we go down really quick, hit normal CDF, press enter. The lower bound for that area was 0.68. Oops, excuse me, that's not an 8. There we go, 0.68, perfect. The upper was 1E99. So I'm going to clear this really quick, press clear, and I'm going to type in 1. I need the E value. Now be careful, it's not the capital E. It's kind of tricky, but it's the blue double capital E. So I'm going to access that. So I'm going to press second, comma, because the comma is going to access that double E. There we are. So 1 capital E 99. There we go. Press enter. Mean of 0, standard deviation of 1, paste. That entry should look exactly the same. Now, if you mistakenly put the capital letter E here, when you press enter, your calculator is going to say error, and it's not going to know what to do because you inserted a letter instead of the actual notation that it needs to use for scientific notation. So we press enter, and here's our probability. 0.248. So we're going to write that out. 0.248. Here we are. So there's a probability, approximately 0.248. Nice. Now let's see if we can get the probability for part C. The probability for part C, again, what we're going to do is we're going to take the exact same approach. We want to start labeling the standard normal distribution using the values that we know. Then we want to identify the two z values that they're giving us. So the first z value is the left one, that's negative 2.43. So negative 2.43 somewhere here. All right, I'm going to say this value is negative 2.43. And then 0.88. It's going to be somewhat close to 1. So here it is. That's 0.88. And that means, this notation means that I want to find the probability that's bounded between those two values. There we are. So as I'm looking at this probability, I now want to find this probability, but in order to find this probability, I need to figure out, again, what are my inputs? What are my bounds? So if you'll see here, this area has a lower bound of negative 2.43 and has an upper bound of 0.88. Let's go to the calculator and make sure that we get this done. All right, here we go. We need that distribution. So again, second distribution, go down to normal CDF. There we are. The lower bound that we are looking at was negative. I'm going to caution you here. Do not use this minus sign. My mouse right now is hovering over the minus sign. If you can see this moving, do not use that. Instead, look at the button right next to the enter button. That has the minus sign. In other words, it has the negative symbol. That's the symbol that we want to use when we use a negative number. So I'm going to clear that, and I'm going to press negative, 2.43. Press enter. The upper bound of that area was 0.88. Mean and standard deviation was the same, and we're going to paste this. So as you'll see here, normal CDF, the area that is bounded starts at negative 2.43, ends at 0.88, has a mean of 0, standard deviation of 1. Press enter. There you have it. There is your probability. It's approximately 0.803 as the probability. Awesome. Let's go back and let's write this down. All right, so really quickly, I'm just going to interpret, make sure that whoever's going to be grading this, if it was on an exam or if it's something that we're using, then we're telling them we're using normal CDF to calculate this, and these are the bounds that we have along with the mean and standard deviation, and the probability that we get is 0.803 approximately. Awesome. So now that we get a little bit more comfortable with this, we can then start seeing that these probabilities can be interpreted quite easily so long as we deal with, or so long as we work with, the standard normal distribution. Now, let's look at a quick fun fact, right? So this is going to be like a Mr. Castro fun fact. All right. So you remember the empirical rule that we saw here. All right, let's look at that empirical rule. I'm going to write on the margin here. What if I wanted to find the probability of this continuous random variable? Let's say that my z-scores were between -1 and 1. So still using standard normal distribution. Let's see if we can find the probability of the z-scores between 1 and -1, and then we'll go with the probability that the z-scores are between 2 and -2, and then we'll also do -3 and 3. In other words, 1, 2, and 3 standard deviations. And we want to use the calculator for this. All right, so let's go back to that normal CDF then. Second, normal CDF. Here we are, distribution. Now I said I wanted a standard deviation, or the bounds to be -1 and 1. Mean and standard deviation are 0, so there's the first one. Let's press enter. Look at that, 0.68. As a percentage, what would that be? 68%? Approximately, because it's really 68.3%. All right, so empirical rule was kind of spot on, saying, hey, it's approximately 68%, but now normal CDF gets us an exact probability, and the exact probability is this on screen. Well, let's see if we can work the rest of them out. All right, I want to use that normal CDF again, and I want to go from -2, oops, there we go, to 2. Press enter. There we are. Approximately 0.954. So would you agree that the empirical rule says 2 standard deviations? Well, 2 standard deviations, empirical rule said approximately 95%. This is really 95.4%. Interesting. So let's work on the third one then. And let's see what we get for the third standard deviation. See if the empirical rule was spot on. Now, we kind of know the spoiler alert here because we've, again, empirical rule automatically know what to expect. But now let's see if it was spot on. 99.73. So approximately 99.7? Sure is. So this then tells me that using the empirical rule as an approximation, that was actually really good. But now we have a better method, which is using the normal distribution. Awesome. So that was my little fun fact as to how to tie in the empirical rule with the normal probability distributions. Awesome. Now we're going to work on different examples down here. All right, so what we're trying to do now is we're trying to find the z-score that is going to be associated with a certain percentile. Now, the percentile that they're giving us here is really the probability that is being given. So 15th percentile, if you remember, we had notation for that. That was p sub 15. And what this means is that if we're looking at the 15th percentile, then this is really just 0.15 or, or 15%. All right. So 15th percentile, 15%, which means 0.15. Now, what does that mean for us? What that means for us, this means that this percentile or this percentage is the area under the curve that we want. And this is a cumulative area. So a total of 0.15 is what we're looking for, or in other words, a total of 15% of the area under the curve. All right. Now, what I'm going to do is I'm going to go to GeoGebra and show you a quick simulation to determine how that area is then going to be calculated, or how we're going to be interpreting it. All right. So here we're on GeoGebra. And what I want to do is I want to start looking at this area underneath the curve. Now, for this area underneath the curve, I have this marker here that says A is equal to 0, and that's going to stand for the area. So what I'm going to do is I'm going to start increasing the upper bound. All right, currently the upper bound sits over at -3 along with the lower bound. And so I'm going to start increasing that upper bound. Now, watch what happens as I start increasing that upper bound. The area then starts accumulating, and it starts accumulating to give us this total area of 0.18. And we keep on accumulating that area. Notice that we get half of the area here. And again, that should make sense because this is symmetric. Half of the bell curve should contain half of the area. And we can keep going, 0.81. Keep going all the way to the very end, and it should give us a total area of 1. So when we're looking for the 15th percentile, the 15th percentile was just referencing 15% of the area, which should be somewhere around here, around the -1 for the standard deviation. And we're going to go through and we're going to make that those findings as to what is that z-score. All right, so again, I want to find a z-score given this area. All right, so let's go back. All right, so here we are. So we want the 15%. And again, I'm going to go through and I'm just going to start labeling this. So this is 0, 1, 2, 3, then -1, -2, and -3. All right, so now that I have this, what I want to do is I want to identify where is that 15th percentile. So the 15th percentile, I am only going to make an educated guess here. All right, so making an educated guess with that 15%, I'm going to say it should be somewhere around here. Now, I could have made an educated guess, and I could have said, hey, maybe it'll be all of this here, stopping here. Maybe it's all of that. At the end of the day, again, it's just an initial guess. Once we get the correct answer, we'll go ahead and we'll go back and modify it. Erase a few things, making sure that we get it correctly. All right, so we want to find the z-score. So in other words, we're looking for these z values down below. So according to our work, and I'm going to go back over here, according to our work, what is it that we want to use now? Well, we don't want to find an area because we're given an area, and instead we want to find a z-score, which means we're going to use this embedded feature on the TI-84. All right, so we're going to use that embedded feature on the TI-84, which is going to be the inverse norm. All right, so I'm going to need to go to second, again, VARS to get that distribution, and then I'm going to go to inverse norm. So there's a few things that we then need to input, and we'll get to that in just a little bit. So really quickly, let's go to the TI. All right, here we are. We're going to access the distribution, so second distribution, and I want inverse norm. Inverse norm stands for inverse normal, which means if you took an algebra course, the inverse just means it's going to undo the function. So inverse norm, here we go. Press enter. I need an area. So I'm looking for the area underneath the curve. What was that area? Well, that area, according to what we have, was, 0.15. There we are. Enter. Mean was 0 because we're dealing with a standard normal distribution. Standard deviation was 1. And what type of tail was it? Was it a left tail? Was it a right tail? Or was it a probability for the center? Now, if you remember the drawing, this one should have been a left tail. So we press enter, and it should paste this. Yes, enter. There we are. So, area under the curve, mean, standard deviation, and it's a left area. Press enter. There it is. There's our z-score. Negative 1.04. Remember, z-scores are always rounded to 2 decimal places. Always keep that in mind. So negative 1.04. Let's go back and write that up. All right, here we go. So negative 1.04, so negative 1.04, so it should be somewhere around here. So again, my initial estimate was incorrect. And again, I said it's okay if it's incorrect, because again, at the end of the day, we can always go back and modify this. So I'm going to modify this. I'm going to erase this area here. And you guys are doing math in pen or pencil, right? Because math should always be done in pencil. All right, and there we go. And we modified it just a little bit. Perfect. So in order to find the z-score, we had to use inverse norm. And we did the area underneath the curve, 0.15. Mean was 0, standard deviation was 1, and we used the left tail for this. And left tail because, again, we're looking at the left tail here. And we were able to get the z-score to be negative 1.04. And that's all there is. Great. So let's look at the probability for the next one. I want you to give it a shot. So give this example a shot. Do part A, and then we'll talk about part B together. So put pause on the video really quickly. Put pause and attempt it on your own. All right, so I hope you gave it a shot, and here's a question. Now, we got to be careful here because in this question, we were asked to find the probability, not to find the z-score like we were in the previous question. So finding the probability, again, I went through and I denoted everything that we were given with that z-score. There we are. And this is the probability that we get. Now, would this probability here be any different? And the difference in these probabilities is the inequality. Less than or equal to or equal to. So would it be different if we included an equal sign? The big answer, no. It would not be different. The thing about inequalities here, whether we have an equal sign or a not equal sign, meaning a strict inequality, the continuous probability aspect about this would still guarantee that even though we use an equal sign or not use an equal sign, the probability is going to be exactly the same. Which means, notation-wise, it doesn't really matter if we use equal signs or not. So, we could come over here to this problem here and then type in equal signs right below here to see if those equal signs change anything, and they won't. They will not change anything. This, again, only works when we're talking about a continuous probability distribution. All right. So, in this example, we want to figure out that, or we want to find the z-scores that separate the top 10% and the bottom 10% of all values. So we're going to assume here that we're working with a standard normal distribution. There we go. Standard normal distribution gets us a mean of 0, standard deviation of 1. Now I want to separate my top 10 from my bottom 10 values. So I need to find out, and again, this is just a rough estimate. I don't know if this is correct or not. We'll adjust if it's not. Area to the right and between -1 and 2. All right, we'll go here and we'll say there. So this is 10%, and this is another 10%. So we're separating these values here, all right? And we want to find those z-scores. So let's see if we can find these two z-scores. Now, you might be saying, hey, there are different ways to do this, and you'd be completely right. All right. Now, one of the methods that I want to use is I want to use this part here. I want to use to shade this. If I've already used the bottom 10% and I've already used the top 10%, how much is left over then? How much is this shaded area in between if they all total to 100? Well, yeah, you're right. That's just 80%. So what I'm going to use is I'm going to use this 80%. And again, what I want to find here is I want to find the z-scores, which means if we want to find the z-scores, we're going to use inverse norm. So to use inverse norm, we need to know the area. What is the area that we're working with? What does it mean? What is the standard deviation? All right, in order to do that, we need to go over to the TI. So let's go ahead and do that. All right, here's a TI. We're going to access that distribution again. We said we wanted inverse norm because we were trying to calculate these z-scores. Area. Notice down here, before I go down to, before I do area, I have left, center, and right. I want to use the center calculation. How much area is in that center? Well, we said that was 0.8. Mean standard deviation is the same. And I want the center, so I'm going to press that one. And I'm going to go and paste it. There we are, paste. So area, mean, standard deviation, and then I'm telling the TI that I want the center value. Let's see, there we are. It tells me these two z-scores. Now, could you have done it differently? Could you have done inverse norm for the area to the left and then used left? Sure. You could have done 10%, 0, 1, and then left. It would have given you this z-score. Could you have done it to the right? Yes, you could have. You could have done 10%, in other words, 0.1, then 0, then 1, and then said this was to the right, and it would have given you this z-score. But in this case, it gave us both of them because I'm asking for a center area. In other words, it's going to give me two z-scores automatically. So these z-scores, again, rounded to 2 decimal places, they're going to be 1.28 and -1.28. So let's go write that down. All right, here we are. So we had -1.28. So -1.28, that should be somewhere around here. -1.28 and 1.28 should be somewhere around here. 1.28. And there we are. So I'm going to adjust my screenings here, my values. There we are. And let's adjust this one too. And there we are. Now we've adjusted it and it looks better. So that inverse norm, what I wanted was that 80% in the middle area, mean, standard deviation, and I used the center function. There we are. And that gave me positive and negative 1.28. Perfect. Now, this is going to be very important here, that the specific notation that we use, that z sub alpha, is a critical value that denotes a z-score with an area of alpha to its right. Very important this is always going to denote an area to the right anytime that we have this type of notation. So this type of notation, how we use it is like this. I'm trying to find a probability, or in this case, a z-score. I'm trying to find a z-score where I have that area to the right. So, here we go. This means find a z-score with a given area of alpha, which is 0.05, and this is to the right. So that's a lot of verbiage that's packed into that little notation there. Find a z-score with a given area of 0.05, and that's designated to be to the right. Well, area to the right, look up here, that was 10%, so we're going to go a little bit less than that. So let's say the area to the right was somewhere around here, and that was my 0.05. In other words, 5%. So if we want to find a z-score, anytime that we find a z-score, we always use inverse norm. All right, the area that I'm using is 0.05, mean, standard deviation, and I want this area to be to the right. So let's go to the TI and input this in. All right, we're here at the TI. Do inverse norm. There we are, inverse norm. The area was 0.05. There we are. The area was to the right. There we are. Let's paste. There we are, 0.05, 0.1, right, enter. There it is. The probability here, or sorry, the z-score is 1.64. So 1.64, again, z-score is always rounded to 2 decimal places. There we are. So this z-score is 1.64. And that was at 1.64, which we'll say it's right here, 1.64. There it is. And we're going to be using this notation a lot as we progress through the course. So we use this part here quite often. So it's going to be very, very important that you know how to do this from now on. All right. And I'll actually leave it at that lesson for today. So again, if you have any questions, Canvas will be open for questions. All right. I hope you guys enjoyed the lesson, and I'll see you all next time.